Hello, everyone. I'm Sudheesh. I'm here to present about a new API for high-performance access to data. So the agenda is we're going to talk about the mesh of systems and applications that are involved in providing analytics to end users like you, and how the data layout is within each of these system and applications, and how across the systems the communication happens, right? And we're going to talk about one of those communication APIs, which is ODBC, and a new one called Arrow, which is what we've worked on extensively. And I'm going to show concrete numbers in the demo. All right, on the high-level picture, on your right, we have data storage systems, which is where the data enters your business's infrastructure, right? And on the left, we have applications, which is what the data analysts use, right? And between, we have execution engines that provide algorithm capability, right? They can run queries. They can interact with the systems that are actually storing the data and provide, for example, functions that you can run in Python, right? So the storage systems are where the data enters your company's infrastructure, and the applications are what you're interacting with. So the data flows from the right to the left, right? And your control messages flow from the left to the right. So when you ask for, when you run a query in Python, for example, the control messages go through the execution engines to the data storage systems, and then the data flows the other way around, right? And there's no strict lines between the types of systems and applications. For example, Python does execution as well, right? And something like Dremio can actually do both provide an application interface and it internally has an execution engine built in, right? And something like Redshift can actually store data and provide execution capabilities. That is, it provides SQL API. The key thing to note is from the time the data enters your company's infrastructure to the time you consume is what defines your time to insights, right? So if you want insight into your data, if you have an ETL pipeline in between, well, that's going to delay how quickly you can react to it in your applications, right? And another thing could be, for example, like how do I discover all the types of data that's the company's collecting, right? So now, if it goes through some cleansing and all of that, then you do not really have a picture of like all the types of tables that you have access to in your applications. So the longer it takes to gain insights into this kind of data, the longer it takes to actually make it. May not be worth it, for example, right? If you've reacted very late to what the information you're gathering is. So from an analyst point of view, I'm looking at data as tables. I'm looking at them as graphs. I'm looking at them as dashboards, right? As a storage point of view, I'm looking at data as how do I store this most efficiently for access, right? As an execution engine point of view, how do I, for example, like make this use SIMD instructions to make the processing go faster, right? But if I'm looking at it from a data engineer point of view, right, it's going to be how do I make these pipelines more efficient so my users can consume the data faster, right? Or if I'm looking at it from a data administrator point of view, how do I restrict access to different users based on their roles in the company, right? Or how do I provide authentication and encryption capabilities? All right. So as I said, in this mesh, the data goes from right to left, and queries go from left to right, right? And another way of thinking about this is each component in this mesh has input and output, right? For example, S3's input is files, right? Someone's writing the data to S3, and output is, again, read API to those files, right? For example, for Pandas, the data input is from various sources that it can connect to, and the output is data frames, for example. Something like Dremio actually can connect to any of these storage systems and provide any of these storage systems in S3, Redshift, and Elasticsearch, and it can provide REST API, JDBC API, ODBC API, and the new Arrow API, which is what I'm going to describe. All right. So that was the query path, which is we are sending control messages throughout the mesh of systems. And now let's talk about the data path, right? So the data path, first, the data might not be clean enough. So there's going to be people who are going to clean up that. There's like data engineers who work on those pipelines and try to clean up the data for easy consumption. And the actual algorithms you run through Python, right? Which is basically, it could just be SQL queries that you submit to these databases, right? And those SQL queries eventually get converted to like filters and aggregations, right? And how do those, so they live in different portions of that, right? For example, you could be doing filtering and aggregations in Python. You could be doing it in execution engines. And some storage systems support that, like filtering at the scan level. Some storage systems don't. And so the further you push logic towards where the data is stored, the faster it's going to be, because the data flowing this way will be lesser in size, right? Smaller in size. So what are the other things that delay data transfer from left to right, right? Sorry, right to left. For example, there's network transfer, right? So from one system to another, if they live on different hosts, well, you have to transfer the data from that to this. This is going to add to your time to insight, right? What else? For example, if they don't speak the same language, for example, like Redshift internally might represent data differently than what Python represents internally, right? So when Redshift sends data, you have to serialize it over the wire, and then when Python reads it, it has to deserialize it into a format it understands so it can manipulate the data, right? So we have all these things that are working against how fast you can get insights into the data, right? And another way of thinking about the same concept of like serialization, deserialization is you're making a copy of the data, right? So you've scanned the files in S3, right? And you've converted it into a format that, for example, Dremio can understand. And then once you've given it to the client is going to convert it again, right? But every time you're making a copy of the data, right? And that's very expensive. When we're talking about kilobytes, gigabytes, it may not be that expensive. But once you go higher scale, it is going to be expensive because you're going to make those copies every time you transfer from one system to another, right? So people try to solve this problem. For example, Redshift and Dremio provide an ODBC API that Python application can consume, right? But the thing about ODBC API is it defines it. It was built in the early 1990s, which is older than me. And it provides an API to be able to connect to the databases to prepare a query I'm going to run to actually execute the query and then to fetch the results, right? So this is the API that it provided, and it's mainly centered on how the clients are going to consume it, right? It's not centered on how the databases actually implement, how the database actually manipulate the data and how they store the data, right? So it was built for something like tables, right? You have rows of like values, and it was built for systems that were just single instances running on one host. They were built for systems that have very few cores, that do not have very high concurrency capabilities, and clearly not for analytical use cases, because analytical use cases do not rely on records. They mainly do computations on columns, right? If I want to do analytical queries, for example, I'm more about like sums, right, which are like aggregations, and maxes and mins, not really look at this person's name and then update the amount of money they have in their bank, right? So the solution to this is if all of them spoke the same language in terms of data, right? Regardless of the initial, so the initial format in the storage could be different, right? You have CSV files, you have Parquet files, you have Avro files, you have internal representations within the system that are sometimes proprietary, right? So those things, the storage could be less efficient for actually running the query, right? What I mean by that is, disks are slow, so once there will be efficient representations of data on the disk that is different from how the data should be represented in memory or how it's represented on the wire, right? But the things in memory and on the wire, by the wire I mean network, right? They are similar because, well, you've already read the data. So Arrow tries to solve this problem by providing exactly that. There's a lot of literature on saying that there is the columnar format for analytical systems is much better than row format. Like I said, the simplest way to think about this is if all the values are next to each other, you can easily sum them up compared to doing random scans on the disk, right? Or in memory, in fact. So Arrow is a set of libraries that actually is used within various in-memory analytical systems. And the biggest thing is once a system is done with its work and it's relaying it onto the next system, we do not have to make a serialization, deserialization if they speak the same language, which is the language of the data in memory, right? And it's built to work with modern hardware in the sense that once you define the format, and if it's columnar, you can use SIMD instructions and all of that. So it is, again, one of the key things, it's language agnostic. So a system written in C++ can talk to a system written in Python or an application written in Java, for example, right? All right. So let's take this table as an example. Traditionally, if it were, well, session ID timestamp source IP, which could be the data coming into your system, into your storage layer. And now if we represent it in how ODBC expects the data to be, well, you first do the first cell of the first row, and then the second cell of the first row, the third cell of the first row, and so on. And obviously, the alternative way is first keep the first column, and then the second column, and then the third column, instead of row-oriented format, right? And imagine if you're doing a min of the timestamps, for example. The last time the user, or max, right? The last time the user accessed would be the last of the timestamps. And that would be easier to load in memory, right? Versus this, which you would have to load the first row and then figure out where that value is, versus just loading those 4 values, and that would just be cache efficient too. All right, and modern data is also, it comes in various formats. It comes in various shapes. It comes in various sizes. And this is, for example, the JSON format. And how would we represent, for example, age next to each other? Well, you can just refer to you have an offset, at least for, let's look at, for example, actually names, right? If the name did not exist, well, you could just have a null vector, right? But if the name did exist, well, you can put Joe and Jack next to each other. And then you can put the ages next to each other, but then you would have to capture how the schema is, right? So once we have a format like this, which is Arrow memory buffer, or a format like this, well, we can actually build a lot of libraries on top, which is what Arrow is. You can build libraries to make arbitrary expression compilation. You can build RPC libraries on top. You can build, you can actually, I'm not very sure about Feather, but you can do, at the scan level on the disks, you can read Parquet files directly into memory, and you can have efficient layers there too. All right, so given that record format in memory, well, we can just put that on the wire as is, right? You first write what the schema is going to be. Well, if you have compression, you also write the dictionary batch, and then you put all the records right after that. And on the other side, the consumer of this data already knows, based on the schema negotiation, what the data looks like. And once they read it off the wire, well, they don't have to deserialize anything because it's already in the language the application or the system understands. Next, what do we need on top? Well, we need an RPC framework on top and an API for that. So if someone says, put this data, you will basically give them the header, which contains the schema. And then you give all the data, and then you say, I'm done. And the server's like, OK. And then if you want the data, you say, OK, this is the data I'm looking for. Give me the data. At first, it sends you, again, the header, and then it sends all the record batches right after that. So this way, once the client or server read the data, they don't do serialization or deserialization because they already understand the format. All right, and now the key thing is, well, modern systems are parallel, right? So you can provide a flight, which is the data that you're looking for, right? So this is, each of this is a flight request, and it's composed of various streams, right? The streams of data might live on different hosts, so we can provide a location, right? And a ticket for that, meaning it could represent that you actually have access to the data, right? So when a consuming application asks the providing system, for example, to give me data, it'll tell you, here are all the hosts which you can scan data from, and here's all the streams that you can scan the data from, right? And for example, if the hosts happen to be in the same data center, right, both the producer and the consumer, they happen to be in the same data center, well, it also improves the network transfer, because it won't be that much delayed, right, versus going across two data centers. So you can have one consumer for each of those streams, and you can basically, even if it's providing n streams, I can still consume them one after another, right? Or I can consume them all at once if I have those many consumer side stream consumers. Or if you have fewer, well, you can throttle those requests and whatnot. All right, so now first we solved how the memories, how the data is going to look in each of these systems, right, internally. And then we've solved how the data should be transferred across these systems and applications, right? And well, we can even horizontally scale the streams, because each stream endpoint could be consumed by one specific consumer as well. All right. Time for the demo. Well, in Python, what does this mean? I have all right, let me show you the setup. Well, so I'm running Dremio local. Dremio is a system that provides a flight endpoint, right? Any system that implements that API could technically provide a flight endpoint, and Dremio is one of those systems. So what I did is I have a JSON data set that basically has a bunch of numbers. I think this is one of the TPCH or TPCDS data sets. And it's in JSON. Now I've applied the JSON format, and this is ready for consumption through any Python application, right? For example, I can connect through a PyODBC application that opens a connection to Dremio, and then it runs the SQL, right? And then fetches all the results. And after that, you have the data frame, and you can manipulate the data frame however you want. Well, similarly, some people there is also something called Turbo ODBC, which underneath the ODBC driver uses Arrow as a representation. But again, there is the problem of converting it into an API that the consumers can understand, which is ODBC, right? Which is the thing that is making it slow. And then this also is the same. Well, you open the connection, you execute the query, and you fetch all the results. Flight looks similar. So this is just for authentication. So we can skip that part, right? So you open a flight client, and you can authenticate to it, and then you're getting the data, and you can immediately convert it into a data frame, and you can do whatever with it, right? So let's see. Let's first run the PyODBC application. Well, this is going to scan the JSON file, right, into an in-memory representation. In Dremio's case, it is Arrow. So it is still there's an initial scan time duration that we're actually spending, right? And then it has to send to the client application. Well, I chose a very simple query, just a select star, right? Because, well, that will still prove the point, right? Because you're doing a data transfer, and you're doing a serialization, deserialization, all of that. And then Dremio sends the results via the Python API, so the PyODBC library, and it's consumed on the other side, right? So, well, that took 32 seconds. We will see what that means. Now let's run through Turbo ODBC application that does the same thing, but its internal representation now is Arrow on the client side, right? Well, this should be faster because there's a lot of optimizations that went into just building this library, right? But it's still, again, at the end, provides an ODBC API, so we have to do a copy convert. So clearly, it's faster than the Python native one. And now let's use the Flight app, which basically just uses the Flight API, and still at the end converts to a data frame that analysts typically use. And this should be faster. All right, so let's actually break down what each of these times mean. So, well, this took 11 seconds, so where is now the 11 seconds spent, right? So we can look at, for example, profile for this, and what it shows is, actually, let's go to the first one, which is 32 seconds, 31 seconds. Let's see what it did for 31 seconds. Well, it shows that we had to scan the table, right? We had to scan the JSON file. It took 11 seconds to scan that, right? But then it was spending the remaining time somewhere, right? So the remaining time is actually spent in, where did it go? Blocked on downstream. Downstream is the application, and it was mainly spent in converting the buffers into an ODBC representation, right? And like I said, Turbo.
I think I missed it. Are you submitting all of the queries to the Dremio, or is it a separate application?
So this is queries to Dremio.
Queries, okay.
So within Dremio, right? So Dremio has an execution engine built in, right? So it can scan the JSON file and provide a SQL API on top, right? So
you are using the SQL API on top of that?
Yes, I'm using the SQL API. So Flight only provides how to deal. Flight says, "Give me data," but it doesn't know what that data represents, right? So, for example, you can say, "Give me data from this file," right? You can just give a location and give you that file as is, or you can give it a command. And in this case, the command is a SQL query, right? And the endpoint on the other side, which is on the Dremio side, understands the SQL command, and it's able to run that and provide the Flight results, right?
But internally, the application that you showed is going to be the application that is going to be executed on the client side.
Exactly. So this is on the client side, and this is on the host, whichever is running the queries, right? So as you can see, most of the time was spent waiting on downstream. Downstream is typically, if you consider data flowing from in a river, upstream is where the data started, which is the storage systems, and downstream is the applications, right? So that's what this little thing is, and it spent almost 19 seconds in the application, right? On the other hand, we have 17 seconds, which is what the Turbo ODBC app took. And in this case too, it'll be faster, but again, most of the time, where did it go? Most of the time is spent, there's 11 plus 6, I guess, is spent again in the application, right? Something like Flight, well, they've already the application already knows what the data looks like, so there should be no time in the application itself, right? And all the 11 seconds were actually spent scanning the JSON file, right? Reading from disk. So you can imagine this is a single threaded application, right? You could have a multi-threaded application that scans all of these streams at the same time. Say, for example, you had partition data with file per date, and you want to consume all of these at the same time in your Python application. I haven't worked with multi-threaded applications in Python, but again, each of those threads would consume a different stream from each of those hosts. So back to this, as long as most systems adopt Arrow's representation of data within their memory and how they communicate with other systems, this is going to do great, because we know columnar analytics could benefit a lot from laying the data out in a certain format, right? And there's actually a lot of involvement within the various communities to move to this format and contribute to the various libraries that you can build on top, including Gandiva, which is a just-in-time compilation for any expression on top of a column, for example, right? And when you lay out the data right next to each other, well, SIMD becomes much easier. But something like Java, you can't use those instructions, so you would have to write converters into C++ and use native code to make the calls, right? All right, that's all I have. There's more information about this on the Apache Arrow community and more also about Dremio on these links. Questions?
The last example that you showed, that is when the SQL execution is happening, does it automatically convert to the arrow format? How does that work? So you still convert into a data frame.
Mm-hmm.
How do you access that so that you are not paying any kind of conversion within the application? Does it automatically, when it is executing the SQL command, does it automatically know how to translate those buffers or whatever the file read is outputting into arrow format automatically, or is it actually reading a number of pull-ups and then somehow internally optimizes and then converts into the arrow format?
So this endpoint is on the system side, right? Mm-hmm. So as soon as you've submitted a SQL query over the wire, right, and the results are coming back in arrow format. And now there's actually a Python library called PyArrow that directly is able to provide you, once you've read it off the wire into the buffers, this Python library basically lets you access that directly. So there is no conversion after that.
So you submit the query and the server knows what the query should convert into. So everything is happening on server. Client just returns the data in the arrow format from server side.
Right. Mm-hmm.
So the arrow and memory formats, of course, random access, right, through the data points.
Mm-hmm.
Do you have any support for that in sort of the cursor implementation that you did, where rather than say fetching all of that data from your data source, where you could sort of instruct the data source to sort of move through those data to specific cursor points and just pull the things you need without reconstructing a new query every time?
I see what you mean. So as you're consuming the stream, you realize that, for example, that you want to seek to a different location, right, on the server side. I wonder how the skip would work. I don't think there's support for that because it's just a put and get API, mm-hmm. right? To put and get stream API, but then it doesn't have a support for like skip this much. Maybe I can see the enhancement should not be that hard to implement. Any more questions?
I have one more. So the Arrow library, so if I want to use indirect shift,
Mm-hmm.
right, what does the database that I'm trying to connect should implement for Arrow format? Does it need to be somehow this middle layer where you have the kind of database and then a middleware that will actually does that conversion somehow, or you just use the library itself in the client and then let it basically handle all of that optimization and conversion from the database side?
So ideally, you want conversions happening on the server side, right? No, there's more resources there and all of that. And in this specific case, if Redshift adopted the in-memory format to be Arrow, then there is no conversion after that, right? But if Redshift has its own internal format, then it would have to convert to the Arrow API to be able to provide this endpoint that the client applications can use.
For that type of like proprietary database like Redshift, you cannot really work around that piece, I would imagine. But
Yes.
if you are using something like Postgres or something that you can implement on top of the database, is it possible to embed, so to speak, Arrow into the database piece?
For sure. I think there are more systems that are adopting the format because they see complete value in making data the API, right? Like if the client and server understand how the data is laid out, well, you don't need to change anything about it. You don't need to copy, serialize, deserialize, and all of that, right? So there are many other systems that are adopting. So this relies on engineers everywhere to realize that this is the way to go forward, right? And it's not just, Arrow does not just come with the layout, right? It's not just a specification. It comes with all the libraries on top that you can use to build your systems, right? So, and those libraries are what people contribute to. In fact, there's libraries for even, I think, NVIDIA processors that I don't know if I have anything about that here, but I think even NVIDIA has a team that's working on how do we make specifically like Arrow computations faster, right?
And the last question I have is, you showed an RPC. Do you think you can expose all of the databases in some API format so that RPC will immediately get the data flow as it is? So the client that you showed is very similar in my mind, an API endpoint where you send an arbitrary SQL command and it returns a piece of data.
Mm-hmm.
Does it support natively that type of RPC to HTTP conversion or anything like this, the Arrow Flight API?
So Arrow Flight itself is built on gRPC, which is built on top of HTTP2 as the API. So you don't have to technically use the data layout as is. You could still convert it into messages that that can be used by any application, right? So at that point, you're converting it into, you still have a conversion from what's in memory into a protobuf message, for example, that the clients can understand. But if the clients also natively support Arrow, then they can use.
But assuming it is RPC, then client should be able to get that data because it is going to be RPC communication, right?
Mm-hmm.
So client still doesn't. Does client still need to do anything in that communication piece? I do not understand the difference. So can you go back to the gRPC piece?
Yeah,
this one. So both the example that you showed as well as this piece says basically the RPC, right? It is the connection is gRPC.
Right.
So in my mind, right, you are sending a arbitrary SQL command, and the tables themselves can be, basically API endpoints.
Mm-hmm.
Does it support anything that natively, so that you don't have to write any wrapper on top of what you provided in here, or you still need to do some sort of that type of, conversion between, if you want to return JSON, you still need to write, JSON converter or protobuf or any type of data format.
Mm-hmm. So at that point, I think the library natively supports converting to protobuf. So instead of running command and trying to get it as a stream, you can get them as messages.
Okay.
And on top of that, I think you can actually build within the library that's not there JSON support, right? So it would, even though it's a protobuf message, you can quickly convert it to JSON and expose it to the application.
Okay. And it will all happen in the server, in the example that you showed, or on the client?
Good question. I think it probably happens on the client.
Okay.
That's deserialization, yes.
Do you ever persist anything to permanent storage in the Arrow format, like rather than going to Parquet or something, so that you could use memory map files or something to sort of very quickly?
Good question. So we do use that internally, but there is no library on top to provide it as a public API.
But you found success doing that?
Yes.
So
It's almost like Parquet.
You could have just stored the arrow.
Exactly.
Right.
Right. But it's still, I don't think so there is converters from Parquet to Arrow, and Parquet is a more popular format in terms of storing columnar data. So that made more sense for most community users to add as a library than just storing Arrow. But there's no reason to not store Arrow in memory or in disk. It's maybe more the things that are writing to storage systems have not adopted that.
One other question. Sorry. Do
No,
you do
go
any
ahead.
compression inline in your driver there? It's highly compressible, right?
Yes, exactly. So once you have columnar representation, it's actually very highly compressible because all numbers are together and there's repetitions there. So that is exactly what the dictionary patch provides. So you can first negotiate the schema, you can provide a dictionary of all the values, and then the record batches. Now your data is even smaller than what it should have been.
So it's baked into the arrow flight specification then?
Yes, it's baked into the specification, and it's also built in quite a few. I think it's built in most bindings.
Very cool.
In fact, I think, well, if the client doesn't support dictionary batch as a thing, the server can, they can negotiate and say, server, you send me only record batches. I don't understand compression. More questions? All right, that's it from me then.